Welcome. In this video, we look at section 4.3, Properties of Functions and Set Cardinality. This lesson will be split into 2 days, and today we cover day 1, invertibility, one-to-one and onto, and then some proofs about functions. 1. Invertibility. Here's our definition. A function f from a to b is invertible if there is a function f inverse from b to a such that f of x equals y if and only if, what do you think? F inverse of y equals x. Here's an example of an invertible function. F is a function since every element in the domain is mapped onto some element in the codomain, and by finding the inverse relation, that switches the domain and the range, and now on the right side we have the domain, and in this case, every element in the domain is mapped to some element in my codomain. Here's an example of a relation that it's a function, the g is a function, but in fact there's no inverse function. And we can quickly see if we try to reverse arrows, then for example the 3 would be pointing to 2 different elements. That doesn't work. And 4 wouldn't be mapped to anything. So it fails on a couple of counts. So there can be no inverse function. Invertible functions have 2 nice properties. F is one-to-one if distinct elements in the domain map to distinct elements in the codomain. Let's look at these 4 examples and see which ones of these are one-to-one. The first is not one-to-one because I have 2 distinct elements in my domain that get mapped to the same element in my codomain. Not one-to-one. How about the second case? Oh, it is. So that is one-to-one. Third case, no, we have a bad situation there, so not one-to-one. And in the last example, yes, that is good. That is one-to-one. Any pair of distinct elements in my domain gets mapped onto distinct elements in my codomain. That's one-to-one. F is onto if every element in the codomain is the image of some element in the domain. So let's go through these 4 examples and see if these examples are onto. And in the first case, it is not onto because we're missing. There's no arrow that goes to this particular element in my codomain. The second example, look at that. We still have something that's being missed in my codomain. So again, this is not onto. Third example, oh, look, it is. Everything in B is the image of something, so this is onto. And in the last example, I'm looking at my codomain. Every element in the codomain is the image of something, so that is onto. So from these 4 examples, we can see the 4 different situations. They can be, a function can be neither one-to-one nor onto. A function can be one-to-one but not not onto. A function can be not one-to-one, but onto. And then here it is, the nice best case of all that makes us smile. Here's an example of a function that is one-to-one and onto. This is exactly what we need for an invertible function. Okay, here are 4 examples. In the first 3, the functions that I'm given fail being either one-to-one or onto. They're not invertible somehow. In the 4th example, it is invertible. Pause the video, take some time, look over these examples. For the first 3, see if you can figure out why is it not invertible. For the last one, why is it invertible? What's the inverse function? Okay, pause the video and give it a try. All right, I will now talk about this. Let's take a look at the first one. The function g, from the integers to the natural numbers, defined by g of n as the absolute value of n, is not invertible. How about a quick example? How about g of -5 equals g of 5? Because they're both the same. The absolute value of 5 is 5. They both equal 5. So I have 2 distinct elements in my domain that get mapped onto the same element in my codomain. How about, oh, so this function is not one-to-one? Is it onto? And in fact, the answer is yes. And you can sort of verify that for yourself. Second example, the function h from the real numbers to the integers is defined by h of x equals the floor of x. This is not invertible. Why not? And so, by the way, the floor function works. It rounds down. So the floor of 5.2 equals 5. And also for integers, like the floor of 5 is just 5 itself. But maybe there's my example. I inadvertently gave the example. It's not invertible. It's not one-to-one. For example, 5.2 gets mapped to the number 5, and 5 gets mapped to the number 5. In fact, infinitely many things get mapped to the number 5, right? Every real number from 5 up to, but not including 6, all of those things get mapped to 5. So very much not one-to-one. Is it onto? I think it is. Yeah, in this case, here's another example. This function is onto. Third example, the function j from the naturals to the naturals, defined by j of n equals 5n, is not invertible. Why not? It is one-to-one, so that's good, but it is not onto. Can I find some number j of n equals 32? Is there an n that works for that? So this is some number in my codomain. That's really how I'm thinking of it. So I'm taking my 32 from the right. I'm asking, is there some number n that maps onto 32? And there isn't, because after this mapping, any result I do is going to be a multiple of 5, an integer multiple of 5. So not onto. And the last example, the function f from the reals to the reals is defined by f of x equals 5x. This is invertible. Why? What is f inverse of y? Well, in order to show the y, I need to exhibit an inverse function. I need to find another function that has the property that these two functions undo each other. So let's propose, let's say that f inverse of x equals 1/5 of x. So then f of x equals 5x, and then f inverse of that, f inverse of 5x equals 1/5 of 5x, which is just x. So it takes me back to where I started. And so I really do have an inverse function. Oh, this is an interesting example. The function g given by this particular rule. Is this invertible? You should definitely pause the video at this point and think about this one for a few minutes. This is interesting. Start it up again and I'll go through it. All right, here we go. Let me just write down some values of z. -4, and then g of z. Well, for my negative values of z, when z is less than or equal to 0, the result is -2z. So I get 8, 6, 4, 2, 0. And then when z is positive, I'll take twice z minus 1. So 1, 3, 5, 7, 9, 11. And of course, this pattern continues on and on and on. And this is kind of interesting, right? Look at this. I'm going from the integers, which is infinite in 2 directions, to the natural numbers, which is only infinite in 1 direction. And somehow I am getting a function that is one-to-one and onto. So it looks like every integer gets mapped to some natural number. In fact, 2 different integers will get mapped onto 2 different natural numbers. And from the bottom, it looks like every natural number is the result of some mapping. So since this function is one-to-one and onto, in fact, it is an invertible function. So even without exhibiting the inverse function, as long as I know that it's one-to-one, check, and it's onto, check, then yes, indeed, this function is invertible. Is it invertible? Create, this is your chance to be creative, create a function f from the integers to the integers that is one-to-one but not onto, and create a function g from the integers to the integers that is onto but not one-to-one. Pause the video, give it a try, be creative. Start up again when you're ready to see my creative work. All right, my very creative work. How about something like this? F of x equals 2x. Not very creative, but this sort of expands all the integers by 2. So the input is all the integers, and the output are all things like -6, -4, -2, 0, 2, 4, and so on. So we're definitely missing a lot of integers. How about the second one? Create a function. Now this one's a little more difficult. Create a function g onto but not one-to-one. So there's a variety of ways of doing this, and in class I look forward to hearing your way of doing it. But here's an example. How about f of x equals the floor of x over 2? So now, how does that work? If x equals, let's say, -2, -1, 0, 1. What is the result of f of x in this case? -2 divided by 2 is exactly -1, so it's exactly 1, there's no rounding there. -1 divided by 2 is -1/2, so that rounds down to -1. 0 stays at 0. 1 over 2, 1/2 rounds down to 0, 1, 1, 2, and so on. So -1, -1, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. You could actually call this a 2-to-1 function, because everything in the codomain is the result of 2 distinct elements from the domain. Formal proofs about functions, and we start with formal definitions. With proofs, the definitions are so important. So here are actual definitions. A function f from a to b is one-to-one if given x1, x2 in A, with x1 not equal to x2, we have f of x1 does not equal f of x2. So that is, distinct elements in my domain get mapped to distinct elements in my codomain. A function f from a to b is onto if for every y in b there is some x in a such that f of x equals y. So that is, for every element in my codomain, there is some element in my domain that maps onto that element in the codomain. And then finally, a function f is called a one-to-one correspondence, or invertible, if it is both one-to-one and onto. Here's a crucial observation. F is one-to-one if f of x1 equals f of x2 implies x1 equals x2. That's kind of the opposite from the definition. The definition said x1 not equal to x2 implies f of x1 does not equal f of x2. So whenever this situation arises, that's exactly what it means for a function to be one-to-one. But we can take the contrapositive of this implication. The contrapositive says if f of x1 equals f of x2, then x1 equals x2. In proof work, this is generally what we use to prove that a function is one-to-one. Here's an example. Let f from the naturals to the naturals be the function defined by f of x equals 5x plus 7. Prove that f is one-to-one. Proof. And it starts right off. Let's suppose that f of x1 equals f of x2. I'm kind of imagining this two-set diagram, and I think to myself, well, maybe there's x1 and x2, and maybe the x1 and the x2 both map onto the same thing. That's f of x1 and f of x2. Well, if that's the case, then 5x1 plus 7 equals 5x2 plus 7. That's the definition of f. Subtract 7 from both sides. Divide by 5. Oh, x1 equals x2. So in my picture, I initially imagined x1 and x2 might be distinct. But what I discover is, in fact, they are the same. So anything that maps, well, no, there's only one thing that maps to that element on the right. x1 and x2 have to actually be the same thing. Oops. There we go. Thus, f is 1 to 1. Here's another example. You try this one. Prove that the function g from the naturals to the rationals, defined by g of n equals 5 over n plus 2, is 1 to 1. Pause the video, write it out, start it up again to check your work. Here we go. Suppose g of n1 equals g of n2, then 5 over n1 plus 2 equals 5 over n2 plus 2. Cross multiply. 5 times n2 plus 2 equals 5 times n1 plus 2. Divide both sides by 5, subtract 2 from both sides. Hey, look at that. n1 equals n2. I was considering initially that perhaps n1 and n2 could be distinct elements mapping onto the same thing, but no, I cannot have distinct elements mapping onto the same object in my codomain. Thus, g is 1 to 1. How about onto? So to prove that a function is onto, here is our key idea. Pick an arbitrary element in the codomain, and then find an element in the domain that maps to it. I have my codomain on the right. I pick an arbitrary element there, and then I have to find something in my domain that maps onto that arbitrary element. Here's an example. Let f be the function from n cross n to the naturals, given this way. F of a pair of naturals equals a plus b. Show that f is onto. So let's just do some examples first so we kind of understand what this function is really talking about. An example would be if I have the pair 5, 3. This is in my domain. This is a pair of naturals, and that gets mapped to the number 8 because 5 plus 3 is 8. And I have the pair 0, 97, and 0, 97 gets mapped to the number 97, and I have the pair 103, and that gets mapped to 103. And so I would say something like f of 103 equals 103. Now, officially, I ought to write f of the pair 103 because now I really see that as an element of my naturals cross the naturals. But we don't ever do that. That's just too many parentheses to worry about. So we just drop the extra set of parentheses and say f of 103 equals 103. So here's how the proof goes. Let n be an element of my natural numbers. So this is my codomain. I'm picking something in the codomain. Consider the ordered pair blank and observe that this ordered pair is in my n cross n. So I need something that maps to n. Well, there's probably lots of things that map to n, right? I mean, if I pick the number 10 in my codomain, I have 7, 3 that maps to 10, and I have 1, 9 that maps to 10. I mean, there's lots of things that map to 10. So what should I choose? And to make matters worse, I'm not just picking a number like 10, I'm picking a number n, which truly is an arbitrary element in my codomain. Well, I feel like I'm going to give away the answer right now, right? So have you thought about this? What should the ordered pair be? Okay, try this one. How about 0n? And observe that this pair 0n is in my Cartesian product of natural numbers. Well, since f of 0n equals 0 plus n equals n, we see that f is onto. So it took a little bit of creativity, it took a little insight to figure out this element in my domain to choose. And that's one of the features of this proving a function is onto. Sometimes it takes a little creativity to figure out the correct element in your domain to use. Here's one. Let f be a function that goes from the positive reals, so another way I might say that is 0 to infinity. Let f be a function from the positive reals to all the real numbers greater than 1 by this mapping. F of x equals x plus 1 over x. Show that f is onto. So I need to start by picking an arbitrary element in my codomain. So something that's greater than 1. So 1 to infinity. All right, now I need some element that maps onto R. What can I find that under this, this definition of f, what will map onto R? Consider the number 1 over R minus 1. Since R is greater than 1, what do I know about that fraction? Oh, well, that fraction has to be positive, right? Oh, well, if it's positive, then it's in my positive reals. Okay, good. So this expression, 1 over R minus 1, really is in my domain. Now let's find what 1 over R minus 1 maps onto. Where does it go? F of 1 over R minus 1 equals all that stuff, and it really simplifies to R. And that's exactly what I want. So I found the thing that maps onto R. Like I said, it takes a little creativity. How did we know to choose that particular number? And one way we might do it is just with some middle school algebra. You might take a look at the function definition, f, call that y. Say y equals x plus 1 over x, and then try to solve for x. Multiply both sides by x. Get xy equals x plus 1. Subtract x from both sides. Xy minus x equals 1. Factor out the x and divide by y minus 1. So we can kind of reverse engineer the function and kind of figure out where objects have to come from. You try. Let f be a function from the reals to the numbers 3 or greater, and it's defined by f of x equals x squared plus 3. Show that f is onto. Pause the video, won't you, and give this thing a try. Let's take a look. Let y be an element of all the real numbers 3 or greater. Consider this. Did you come up with this guy? The square root of y minus 3. First of all, I need to confirm that that thing really is in my domain. Since y is greater than or equal to 3, y minus 3 is greater than or equal to 0, so the square root of y minus 3 really is in my domain. So that's the first thing you need to check. Make sure that this element you are proposing really is in your domain. Then let's apply the function to it, and we find that we get y. So we did it. I picked an arbitrary element in my codomain, and I found something in my domain that maps onto it. This function is onto. All right, a bonus example. You weren't expecting this, were you? Define a function f from the rationals to the naturals by this. F of a rational, q, is 2 to the a, 3 to the b, where q, that rational number, is expressed a over b completely reduced. For example, f of 10/40ths. What am I going to do with 10/40ths? 10/40ths really reduces to 1/4, so I use the 1 and the 4 as the exponents on 2 and 3, and that ends up being 162. Is this function one-to-one? Is it onto? Prove what you can. And in fact, I will stop the video there. In class we can discuss this, but see what you can get, see what you think, and I look forward to hearing what you have to say. That is it for our discussion on one-to-one, onto, and some of the proofs involved.